Our project problem deals with optimization and has three parts, A, B, and C. Our group members are Peter, Sam, Athar, and myself. For part A, it says, let ABC be a right triangle with a right angle at A. Let the hypotenuse, BC, be of length 10 inches. If the inscribed circle touches the hypotenuse at point D, that is, the circle is tangent to the hypotenuse at D, prove that CD equals half 10 plus AC minus AB.
Go.
Given this triangle in the problem, we are going to begin by solving A. The problem tells us that ABC is a right triangle with a right angle at A. As well, the hypotenuse BC is a length of 10 inches. The inscribed circle inside of a right triangle touches the hypotenuse at point D. Thus, the circle is tangent to the hypotenuse at point D. This is shown in the drawing provided. With this being established, our ultimate goal is to prove that CD equals 1/2 times 10 plus AC minus AB. Thus, with the information given, we're going to break up the triangle into smaller triangles with the circle. This allows us to find the values of AC and AB, consequently proving this. We have the radius of this circle, our greater point E, which is halfway or midpoint between say C and A, and the point F. So we're going to prove that this side equals this side first. So we're going to zoom in basically on the triangles. This is C. This is angle theta. This is side is H, the hypotenuse, and then R, which is the radius length right here. So with the two triangles, they are both 90-degree angles. This is 90. And at angle C, there is a perpendicular bisector. This means that it intersects angle C at a 90-degree angle, splitting the two sides equally in half. So 1/2 is angle C. This is split. This leaves us with just angle L. This is 90. Which to the two triangles is equal, because if you subtract 180, which is the sum of all the angles in the triangle, by 90 degrees, we would end up with the same value for both sides. So with the angles all equal, if we did SOHCAHTOA on the side labeled with a question mark, we should have the same length. L would equal H. L would equal H. This ultimately proves that CE equals CD. Now we're going to prove that this side is equal to this side. Which will be the same way we just did. Zoom up on the triangles. This is angle B, right angle, angle X, question mark. Here's the side R, just the radius. So as shown above, the two triangles both have 90-degree angles like the last one. As well, at CB, there is a perpendicular bisector, thus splitting the M equally in half. So the angle M. So M equals 1/2 of CB. Therefore, if we subtract 180 degrees, which is the sum of all the angles in the triangle, by 90 degrees, and M would get equal sides to the last angle. Also, similar to before, since we know all the angles are equal, we can use SOHCAHTOA to prove the sides are equal, that M equals R and M equals R. This proves that DB equals BF. Now BF, and that CE equals CD. We prove that these angles are all the same. Now that we have proven that, we can go ahead and prove that CD is equal to 1/2 times 10 plus AC minus AB. So from this triangle, we are going to split the circle with the radius by the definition of the circle. Therefore, with this, we can find the values of AC and AB with respect to CD and R. So first, AC minus CE is equal to R. So although for this equation we can plug in CD for CE because we proved that CE is equal to CD. We can go ahead and plug in AC, CD plus R. Now to deal with AB, we can create the equation AB equals BF plus R. However, for this equation, we can substitute in BD for DF because we proved that BD is equal to BF. So AB equal to BD plus R. Although this is correct, we want CD and R to be equal to AB. So BD will be equal to 10 minus CD. Alright, so now that we have BD equals 10 minus CD, we can go ahead and substitute that into AC equals BD plus R for BD. So this will be AC equals 10 minus CD plus R. We can go ahead and solve AC equals 10 minus CD plus R. AC equals 10 minus CD plus R. We know that AC equals CD plus R and AC minus CD equals R. So we solve this for R here. Then plug the R into the AB times 10 minus CD equals R equation. So we'll have AB CD plus AC minus CD. Now that we have this, we're going to solve for CD. So AB will equal 10 plus AC minus 2 CD. Then we'll do AB, so we'll subtract 10 over, and we'll subtract AC over. So we'll have AB minus AC minus 10 equals negative 2 CD. And then we'll divide by negative 2 each side. Then we'll have CD equals 1/2 10 plus AC minus AB. So with this, we have proven that CD is equal to 1/2 10 plus AC minus B.
For part B, it says, let theta equal half the angle of C. Let R be the radius of the inscribed circle. Express R as a function of theta. Hint, use your result from part A.
Okay, so for the second part of this problem, we are instructed to let R be the radius of the inscribed circle and to express R as a function of theta. So if we refer back to the figures in part A, the triangles, just give me a second to draw these out. Have C, let's say theta right here. So we have our two congruent triangles right here, and we will be using theta equals 1/2 angle C, and express r as a function of theta, excuse me, so that means we will end up with theta equals angle C over 2, or 2 theta equals angle C. So before we proceed any further, we have to define C through using the practical domain. And for that, simply have to use 0, 2 theta, 90 degrees. This is our practical domain because we already have one 90-degree angle established in the triangle. That's what we're given. And so if we were to have another 90-degree angle, then we would have two 90-degree angles, and if the sum of volumes for a triangle is 180 degrees, that means either the third angle would be 0 degrees, which is impossible, or simply we would not be working with a triangle. So it has to be somewhere between 0 and 90 degrees. It can't be either or, it has to be somewhere between, for 2 theta. Or in this case it would be 45 degrees if you simplify it. But regardless, we can go ahead and put the triangle back into one equation that we just ended up with, again from part A. Now to do this, we're going to be using SOHCAHTOA on theta, and this will be done with tangent, so we will be working with tangent theta equals r over CD. So now we know from part A that CD equals 1/2 times the quantity of 10 plus AC minus AB. So given this, we can go ahead and plug in for CD in this equation right here. So we go ahead and plug that in and rewrite it. And as we do this, we will be solving for r and simplifying the tangent through trig identities. So we're going to go ahead and erase this, rewrite it back as one neat problem. So we're going to be having, sorry if my shoulder is getting in the way, don't really, here. It's kind of a tricky situation trying to work with this. So tangent theta equals r over 1/2 times the quantity of 10 plus AC minus AB. So now again we're going to be solving for r, and we're going to be using our trigonomic identities to help us solve this equation. So we're going to go ahead and rewrite this again. We're going to go ahead, since we're solving for r, so we're just going to do r equals, and then we will have sine theta over cosine theta, because as we know the trig identity, tangent of x equals sine of x over cosine of x. So that explains why a tangent all of a sudden became sine over cosine. And then we're going to go ahead and multiply this by 1/2 10. I'll have to bring this down here. Plus 10 cosine 2 theta minus 10 sine 2 theta. Alright. And then if we go ahead and we simplify this even further, we will go ahead and end up rewriting this problem as r equals sine theta over cosine theta times 5 plus 5 cosine 2 theta minus 5 sine 2 theta. Squeeze that in there right at the edge. Now we're going to be using the following trig identities to simplify cosine squared and sine squared theta, or no, excuse me, sine 2 theta and cosine 2 theta. So we have our double angle identity. So as we all know, we have cosine 2 theta, that becomes, or that is equal to 2 cosine squared theta minus 1. And then for sine 2 theta, we have 2 sine theta cosine theta. So now if we go ahead and apply these trig identities to our equation, we're going to end up with this big fella right here. R equals sine theta over cosine theta times the quantity of 5 plus 5 cosine squared theta minus 1, and that's going to be minus 5 times the quantity of 2 sine theta cosine theta. Of course, this snakes around back here. All right, excellent. And now we're going to go ahead and do PEMDAS to simplify what's in the parentheses first, and we can go ahead and write this equation as neatly as possible, because as we just saw, that was a pretty gnarly equation. So we're going to go ahead and do this real quick. So we're going to go ahead and simplify from the parentheses outwards. R equals sine theta over cosine theta times 5 plus 10 cosine squared theta minus 5, and that whole quantity is going to be subtracted by 10 sine theta cosine theta. Alright, and we can go ahead and simplify this down one further by going ahead and rewriting this once more as R equals sine theta over cosine theta times the quantity of 10 cosine squared theta minus 10 sine theta cosine theta. And now from here, what we can do is, since we have a cosine squared in our first parentheses, we can go ahead and actually remove that, and that'll help us simplify it even more. So we can go ahead and just rewrite this. R equals sine theta over cosine theta, and then we're going to have times cosine theta times the quantity of 10 cosine theta minus 10 sine theta cosine theta. Had to squeeze that in again. We shouldn't have to do that for much longer, because now we can go ahead and simplify everything out. So as we see here, we have cosine theta over 1. We have cosine theta here in this fraction over here. So these two just cancel each other out. Alright, so once again, after we go ahead and cancel out the two cosine thetas, we can go ahead and rewrite this equation now as this. So we have R equals sine theta times the quantity of 10 cosine theta minus 10 sine theta cosine theta. Again, we have to squeeze that down here again. All right, now, well, excuse me, I miswrote that. Yeah, it's all one quantity. So now we can go ahead and distribute sine theta across these two parentheses right here. And we can go ahead and rewrite this once more, as we have R equals 10 cosine theta sine theta minus 10 sine squared theta. And now we're going to use the trig identity on 10 cosine theta sine theta, but first we have to factor out a 5 so we can apply the identity to the function properly. And you'll see what I'm getting at here, so let's go ahead and erase all this work that we just did. Alright, now if we go ahead and factor out a 5 from the equation, we have r equals 5 times the quantity of 2 sine theta cosine theta, right, minus 10 sine squared theta. Okay, and now we can go ahead and apply our double angle identities again. And now we simply have r equals 5 times sine 2, hold on, I messed up. These are two separate identities, or two separate quantities. 2 sine theta, cosine theta minus 10 sine theta. These are completely unrelated to each other now. So now we have 5 sine 2 theta minus 10 sine squared theta. And now this will leave us with the final r function for theta, which is, once again, 5 sine 2 theta minus 10 sine squared theta equals r.
For part C, it says, if the hypotenuse BC remains fixed at 10 inches, yet theta is allowed to vary, i.e. get smaller or larger, find the maximum possible value of r. Hint, use your result from part B.
So for part C, the goal is to find the maximum possible value of r when BC remains fixed at 10 inches. However, theta is allowed to vary. Therefore, the first step is to find the derivative of the equation we found in B. We do this because with derivative, we can find the maximum point in the graph by setting it equal to 0, and then checking by using a sign chart. When finding the derivative, we will be using the power rule and the definition of the derivative of sine of x, which is cosine of x, and cosine of x is negative sine of x, as well as the chain rule. So this will be the equation that we will be doing the derivative of. Now, the equation that we found from the derivative is r prime is equal to 5 cosine of 2 theta times the derivative of 2 theta minus 2 sine theta times sine of theta. And the reason why we do this is because we will be treating cosine of x, which will be cosine of 2 theta, and we will be treating whatever the inside of the parentheses as x, which in this case is 2 theta. And since it's because of that, we will be using the chain rule on that. Now, a similar process is there for sine theta, and however, it is different because we will be treating sine theta similar to x squared. And because of this, we will be doing the derivative of sine squared theta, which is just 2 sine theta times the derivative of sine theta, which gives us if we simplify this, we will get 5 cosine 2 theta times 2 minus 10 2 sine theta times cosine theta. And if we just simplify it further, we will reduce this to r prime equals 10 cosine 2 theta minus 10 times 2 sine theta times cosine theta. Now, to simplify this derivative further, we will be using trig identities for 2 sine theta times cosine theta and set that equal to sine 2 theta. Next, we will set r prime of theta equal to 0 so we could find our critical number. And we divide by 10. And then we divide by either sine of 2 theta or cosine of 2 theta. And in this case, we will be choosing cosine of 2 theta. Which will simplify to 1 is equal to tangent of 2 theta. Now, to solve for theta, all we need to do is use trigonometry, and to do this we will have to take the arctan of tangent of 2 theta and do the same for the other side. The arctan of 1 is the angle on the unit circle, pi over 4. And since tan is equal to sine over cosine, where sine is pi over 4 is equal to y, and cosine of pi over 4 is equal to x, we therefore are left with y is equal to square root of 2 over 2, and x is equal to square root 2 over 2, which gives us tangent pi over 4 is equal to 2 over 2 over 2. And this just simplifies to tangent of pi over 4 is equal to 1. This proves to us that arctan of 1 is equal to pi over 4. So now we can go ahead and plug the value back into arctan of 1. And this gives us pi over 8 is equal to theta. As we find our critical point, we must verify that it is in fact a critical point. In order to check our work and verify this critical point, we must go ahead and make a sign chart. Recalling our work in part B, we know that the practical domain is 0 is in between, C is in between 0 and 90, or C is in between 0 or pi over 4. So the sign chart will range from 0 to pi over 4. And the reason that the sign chart is going to be for f prime is because the outputs for f prime are the slopes of f at the same given input. For example, if the output of f prime is positive, we know that the slope of f is positive, while if the output of f prime is negative, then we know that the slope is negative. If pi over 8 is an actual critical number, then we can actually see the slope of function f of x change from positive to negative or vice versa when crossing either side of the point. We will be plugging in numbers 1 over 4 and 3 over 4 into r prime. And just to save some time, I'll just put in the numbers. And when we plug in 1/4, we will be getting a positive number. And if we plug in 3/4, we will be getting a negative number. And this shows us that there is a local max at pi over 8, which proves that the critical number exists at pi over 8. So thus, theta is equal to pi over 8. Now that we have proven that pi over 8 is our critical number, we can go ahead and plug that into the r equation, which will give us the maximum possible value for r. We will be using the unit circle to solve for sine pi over 4, but we must use the calculator to solve for sine pi over 8 because it doesn't appear on the unit circle. Therefore, r is equal to 2.03106.712. Therefore, r is equal to this, and it is the critical point and thus the maximum possible value for the radius.
For our conclusion, the most significant and important concept to remember from this problem is the derivative. Through use of the derivative, we have been able to find the one possible number that gives us the maximum possible radius for the circle given the conditions. Without knowing of the derivative or how to use it to our advantage, solving this problem would have been nearly impossible.